Okay, so like I was saying, we're going to play in the next couple weeks, this week and next week. We're going to play with some stuff. We're going to build some random things. I've got random components that we're going to fiddle with, and we're going to do stuff. So we're going to start out by kind of learning about square waves. No, we're going to learn about oscilloscope by building. You already have a schematic. We have what we did multiple versions of this. You're going to have to go back to the one that works. It should have been the last one we messed with. Where's my marker? Invisible. But I'm going to give it its official name-ish. So we're making a 555 timer square wave generator. Okay. Now it probably isn't labeled this in your notes. So you're going to have to figure out which one of these it is. Yes, ma'am.
Has, I can't remember her name, Abigail's sister been coming to math class?
Abigail's sister been coming to math class.
Algebra 1 student.
Yeah, she comes one of the 2 days.
Last week?
Yeah, I think so. Yeah, she did.
Okay, well, I haven't since the second week. I haven't seen Abigail, and I just didn't know.
You're talking about Naomi, right?
Yeah.
Yeah, Naomi did come last week.
Great. I was just wondering because I hadn't heard from their mom. I'll just send her a message and check.
Okay. Okay. So, what does a square wave look like?
I'm hoping like this.
Yeah, just like that. Okay. So, you need the 555 timer circuit that looks like this. That makes this sort of signal. Whenever it works correctly, and we get the output on the 555 timer on the oscilloscope, it'll look like this. See that little yellow signal there? Let me flip the camera around. It'll look like that. So that's what we're trying to make. You've made one that worked before. And in case you need a refresher on what we're talking about the one that made the LED blink on and off, right? Because this would be LED is on, this would be LED is off. Which mode of the three should the 555 timer be in?
Monostable?
So what does monostable mode do?
It's a single pulse.
Single pulse, so probably not monostable mode, right? Because that's not a single pulse.
What about astable?
So astable. So you need the one that we did that worked in astable mode. Remember, we did like 3 different variations, and so you need to go the one that actually works. It is the flip-flop one. Okay, so we want to put it in astable mode. Okay, so ready, go.
It was the 9th week.
It was the 9th week, okay.
That helps so much.
It was September 16th.
None of that is useful. Thank you. It is kind, but not useful.
It's disappointing. Remember if it was the first, second, or third one we did?
It would have been the last one we did, right? Because the last one we did worked.
The last one we did was the one with the LED and capacitors.
They all had that.
It was, no, but it was the 3E. Never mind.
Do you know which one it was? I mean, you have the ones for buzzers.
That's true. It wouldn't be that one. Because that one doesn't make the LED turn on and off, right? Astable mode is a really simple mode.
Let's see if this one or this one. I think it's this one. This one. Pretty sure. Almost. I don't know. I'm just pretty sure it is.
You could also use your Google if you want. You're welcome to do that.
2.7.
What is red?
Red is 2, and then purple is 7, and then red's 100. So is that 270 then?
That'd be 27 with 2 zeros, right? Because math.
So I would need
To give you a bit of a hint in your remembering, you want a circuit that is kind of in this form, because this is just like the most generic astable mode. The one last week, remember, is more like it's in bistable mode. Oh, is this? Yeah, that's right. And then chart assumes these R1 is a 10K, is that right? Let me look. Assumes that R1 is fixed at a 10K, yes. You can actually change it, but and dream and sleep. Right, yes. And then forward voltage. This is drawn real stupidly, but you want a circuit like that. C2 is usually a point one, yeah, or something like that. Let's see what See what they use. They use a .01. That's fine.
That isn't in the
Yeah, you have that.
wait, where? Did I not write it down?
What isn't in what? What are you asking?
In this circuit, 5 is connected to nothing. And
Yeah, you don't necessarily have to have a capacitor there, but you can put it in. That's what yeah. So these two are the ones that set your frequency.
in this circuit, it's 10 microfarads.
In which one?
This long linking.
10 microfarad. So you need to increase the, if you want to be faster, you need to either decrease that one or decrease the R2.
Which is the resistance. So it's the variable resistance.
Yeah. Decrease either one or both of those and you'll make it faster.
Oh, yeah. Which is what we want.
Theoretically.
Hopefully. What is 5?
What do you mean?
That capacitor.
0.1 or 0.01 is fine.
Or you said you don't need it.
You could leave it off. You could add it in for stability though.
Stability. So it doesn't blow up or something?
So it doesn't blow up or something? No.
What do you mean stability?
It'll run more stably.
What is that?
It means it'll be more consistent. It won't behave differently. You understand the word stable, right?
Maybe.
You're going the extreme end of unstable. Extreme end of unstable means blow up, but there's a lot of phases between working perfectly and blow up. There's a lot of like layers of stability that could happen in there, right?
Yeah, I guess so.
Yeah, that's
So that's the circuit we need to build.
you need to build something like that, yes. Which is very much what we built last week.
So can
Just use the power supply. You don't need to use the other. You're just testing it with the LED. If you get it fast enough to where the LED looks like it's just on, you're probably in a good place.
What is this output?
It's your LED or the oscilloscope or a buzzer or a whatever, right? Something that I would put an LED in there with a resistor in place so that you can see it for now. And then then you can potentially try it with the oscilloscope and see what kind of things you can get.
Is it 3 connected to the LED to the resistor to negative, or is it like 3 to the resistor to the LED to negative?
It doesn't matter.
It doesn't matter.
No.
I thought it would.
No, because that's all one loop, one branch, right? So it's the same current going from here, this node to that node. So whether you do it before or after, it does the same.
Okay, okay.
That seemed weird.
Juicy.
Most times.
Well, I say weird most times too. What's the voltage supposed to be? 6?
Yeah, you could start with 6 and see what happens.
Must have done something wrong. Because it's just on.
So that's not necessarily wrong. Let's hook up to the oscilloscope and see what it looks like. So with our oscilloscope, no, leave it.
Oh.
With our oscilloscope, this goes to ground, right? This is our ground. And then, so what is this? You're crisscrossing stuff.
Yeah, so it doesn't
Okay.
bend.
And then this, we're gonna just attach to our output. And get us some power. And then just start with hitting audio and see what we see. And it's a square wave.
So it's correct, but how is it? What is it doing?
So it is blinking. It's just blinking so fast that you can't see. It's blinking at 170 hertz.
What does that mean?
Pulses per second.
That's a lot of pulses per
Yeah.
second. But that's what we wanted.
So
right?
one full pulse is 5.87 milliseconds. That's great.
This is what we wanted?
This is what we wanted.
This is what we wanted.
This is what we
Yay.
wanted.
Woohoo.
So you should add, you have, I believe, aren't our, what resistances did you use for R2? Did you use a 10K?
I used yellow, purple, yellow.
So what is that?
47K?
47K, or is it a 470K? I think it's 470K, isn't it? With the yellow multiplier?
No way.
No way, yes way. For R2, between 6 and 7, you use a 470K.
Yellow, purple, yellow, which is to the fourth, 10 to the fourth. So that's 470K.
Yeah, 470K. And that's the one you use between 6 and 7?
Between 6 and 7, correct.
Yeah. And then what do you use for the C1?
C1, that's a 0.1, 0.1.
0.01, or it's a point, or it's a 1?
0.01.
You lost something.
Yeah,
Was
I
it-
dropped
was
the
it
resistor
this?
that I found on the ground. Yes.
Look at you. Yeah, so you should, let's see, you should try changing those values and see what kind of frequencies you can get.
Okay, I'll change the capacitor to a bigger, to a 10
Okay.
MF microfarad. Boom, done. It's really slow, but it's blinking.
It's what?
It's blinking.
Yeah. Oops, that's not the one I want. Yeah, it's there. It's just. Yeah. It's just pretty slow. It's frequent. Does it give us a rare frequency? Doesn't. It's slow enough that it's having trouble doing the math.
So I would speed it up by doing like a lower
Can you-
resistor.
Yeah, the LED is actually, yeah, you can actually see that. At that frequency, you're better off with just looking at the LED. Okay, let's see what you got. Poor little orange jumper. All right, so 1 to ground. 2 and 3. This is a 47 between 2 and 3. 2 and 3, look, 2 and 3, nothing connects 2 and 3.
Oh, I was doing this.
2 and 6 connects.
I was
3.
doing the same one as last week. Do you want me to do that one instead?
Well, this isn't even that really, but yes, for the only the third time, it's okay.
So, can I use this circuit? Can I use the same circuit for next week, or like for powering this one?
Yes,
Okay.
yes, you can. Did you use a capacitor on pin 5, Malcolm, or did you leave it off?
On pin 5, I leave it off. You left, I leave it.
You should try it with a 0.1 and see if it still functions like you'd expect.
Is 0.1 104?
It'd be a 105. No, yeah, 104. You're right. You're right.
I'll do that in just a second.
It should still work just great, but
Why is it doing this? What is it doing?
did you plug your ground in? Move this one out of the way so it's less. Ground is in. What is it doing? Auto trigger something.
It said none, I think, or 1.
Seems like it's too slow still. Yeah, try to go faster instead of slower.
Well, I did went faster.
What?
Is there a limit to how low R2 can be?
So the lowest they list in their table, I'm sure that you could get a lower enough number where it would be not so useful. The lowest number that they list is a 10K.
So you could just get rid of it because there's already a 10K.
No, that would make this split the voltage in half. Because it would be the same. What did I say? What did I say was true? As you increase your resistance, as you increase the resistance, the frequency goes down. As you decrease the capacitance, the frequency goes up. They have an inverse relationship.
I don't know what's happening, John. It's not doing anything.
Did you hit auto?
Am I supposed to?
Yes.
Which capacitor should I use for C1?
It's working, but if you can see the LED blinking, it's too slow for this to be really useful. Don't unplug stuff so other people can do things. What'd you say?
What capacitor should I use for the C1?
I would use the 10 microfarad for now.
And that one's the 106?
Mm-hmm. It is. Oof. At 10 microfarads, between 10K and 1 mega ohm resistor, you can get 4.8 2.7 hertz, 1.4 hertz, 0.69 hertz.
What is this pointing to?
So this always goes to ground, and this gets where you want to probe, so it'd be at the LED.
Can I have a 105 ohm or 105?
A what?
Can I have a 105?
What is it? What actually is that?
1 ohm, 1 microfarad.
A 1 microfarad capacitor. Yes. Yes, you may.
Said ohm like a goofy.
Like a goofy goober. Well, at least you didn't do like my beginning class and say, can I have a 105 banana thing?
What? Did that happen today?
Yeah, it did. So I'll give you the formula. Let me give you the formula. Here's the formula. You have this in your notes somewhere, but the formula for calculating the frequency, astable mode.
We have it in our document of papers, I think.
Well, that may be true. Frequency equals 1,440 divided by R1 plus 2 times R2 times C1. So if we figure out what do you have in there currently at this moment?
As R2 is.
R2 is R1 is a 10K, right?
Yes.
We're keeping it fixed at.
47K.
So 10K plus 2 times 47K, and C1 is what?
C1 is 0. No, wait. 0.1. Wait, what is it?
Probably has to be in,
Oh, it's a 105. It's a 1.
C1 probably has to be in farads, I bet. So it's a 1 microfarad, which would be a how much farads?
0.01?
0.01, he says. So there's 100 microfarads in a farad?
I don't know. Mike, what is a micro? Like,
What is a micro? I don't know, Google it.
with that time, I could just be like, how many microfarads in a farad?
Yeah, that's true.
I
You
don't
could.
know how to spell it, though.
It's spelled like it sounds.
It is.
A million.
A million microfarads.
Holy cow. That's a lot. So a micro is a millionth?
Millionth of a farad. So I don't know for sure if this has supposed to be in farads or microfarads. We're about to find out, I imagine. So you said 1 microfarad?
1 microfarad.
So times 1 over 1,000,000.
Yeah. Let me grab my calculator real quick.
What's 2 times 47,000? 100 and some odd, sounds like to me.
That's 94,000.
Oh yeah, that makes sense.
This is less than
94,000, so 104,000 times 1 millionth. So what's 104 divided by 1,000?
0.014. Or sorry, 0.104.
Yeah, you just move it 3 places, right? 0.104. So 1,440 divided by 0.104 is going to be a large-ish number. What are we doing? What did we have? We had a 47, 470K. I think these are. I think C1 is in microfarads based on these numbers in this chart.
I got 13,846 approximately.
What did we do? We did a one microfarad. So the answer should be 1.5. What'd you get?
I got 13,846.
13,846. 1,846. So, assuming that this was actually in microfarads, this would be 1. What is 14? No, even that still wouldn't be quite right. Let's figure out how to figure out let's figure out what we're doing wrong using algebra. So you said you had a 470K. You're sure it's a 470K?
No, it's a 47K.
Well, we were doing the math on a 44. Oh, just kidding. We weren't.
47K.
We were doing 47. Oh, well, then I'm looking at the wrong place on the chart. 47K and a 1 microfarad, 14 is what they're saying.
That's close to
Yeah, so you got what, 13? Yeah. So that's, yeah. Okay. Yeah, no, it's just, this is not in farads.
maybe it's in
If it's in microfarads,
millifarads or something. I don't know.
okay, so 104,000 this divided by 104 is what?
104,000.
So 1,440 divided by 104.
It's 1,000.
1,440 divided by 104?
440. Oh, okay.
There's no way that's right.
That's about 14.
Yeah. Okay, so that means you would multiply this number times 1 over 1,000, which is a millifarad.
I said that.
You did. Probably in some of the words. So C1 needs to be in millifarads to figure out the thing. Now, and what did we calculate? What is it still running?
Yeah.
What does it say the frequency is?
About 14 a second, 13 a second.
No, on the oscilloscope. Oh, there's something weird happening. There's something that's introduced that's broken it.
Uh-oh. Spaghetti.
You need to put that capacitor back in there. But it says the frequency is about 14 hertz. So yeah, great.
So we got it.
Okay, so
With a mark.
in your notes you should have this, and let's put what units the things need to be in. R1 and R2 in ohms. And you could actually shift this some. Like I bet if you put this in kiloohms, in kiloohms than it would be, yeah, in kiloohms, and that would be in microfarads. Anyway, R1 and R2 in ohms, and C1 in millifarads. And 1 farad equals 1,000 millifarads.
So we're writing down the blue?
Yeah, you're adding the blue. If you want to add this math, you can, but that's not, you need this purple and you need this blue. That'll give you a formula for your frequency. And then when we come back, probably next week, we're going to keep playing with some other stuff. Got some random stuff that we're gonna play with. We may mess with some motors and some other transistor things. But when we come back and we hit our counter circuit again, we can use this to set how fast we want that counter to be changing the things. So if we do it this fast at 15 hertz, it's going to be really quick and it's going to blink through the LEDs real fast, right? I think it's about time to put up. Yeah, it is.